I would like now to invite Professor Mark Crowley, who is going to be our next speaker in this series of presentation. And Mark is going to speak about wildfire management, disaster response, climate change. So let me introduce very briefly Mark. He's a professor with us here at the University of Waterloo in the Pattern Recognition and Machine Intelligence group. And he's a core member of the Waterloo Institute for Complexity and Innovation. He's an active part of building the interdisciplinary computational sustainability research community and blogs on this topic, as well as democratic reform and the impact of AI technology on society. So Mark, we look forward to hearing from you on your insights as related to this research project. Please go ahead, Mark, and if you would like to share with us your...
Oh, yeah, okay, I thought I had already.
Okay.
There we go.
Take your time.
So now you can hear me, right?
Excellent, yes. Thank you.
Okay. I had the wrong microphone on. So many microphones and setups in this thing now. Thank you very much, Fakri, and thanks everyone for setting this up. Right, you can see me, so you can see my screen, right?
Yes, we do, Mark.
Yeah, great. Yeah, so I'm going to talk about some of the work, well, some of the kind of perspective on applying machine learning to some kind of disaster response problems, specifically forest fires and forest fire management, but in the context of this kind of using AI and machine learning for good in general. So let's jump right in. There's obviously a lot of great advances and uses of AI methods and machine learning over the last 10, 20 years. They've been improving it tremendously, and it's going to get people excited, right? They could be playing games, that's cool, finding cat videos on the internet, that's great. Ranking advertisements and making people lots of money is very good, and they can provide money for us to do other research. But people often ask, what can we do that's a little bit more important and actually affects society and the world? So that's great that we have a whole stream on that here for the Institute's talks. And so there's a lot of stuff going on with that, actually. So one thing that people have is a handy map of things that need to get worked on is this United Nations Sustainable Development Goals, which is really a very large set of goals. They boil it down to those that small set of categories, but within each one of them there's very detailed explanations of things that need to be worked on: the environment, society, economics, education, equality. So I've been involved in a few things around the world in the last few years on AI for good and different things that are happening with the sustainability goals. So this is just a snapshot of some things that were happening actually a couple of years ago. It's actually expanding even more since then. Basically, most machine learning and AI conferences now have an AI for good or some variation of those words workshop or stream. And so it's really useful for researchers because we get to be able to say, you can apply your problems or try to find your problems on harder domains that are actually have an impact on things. And it's not just that you have to do something that's going to make somebody a lot of money. And it's also that those problems that make people that you can make money more easily are kind of getting solved and easier, right? So the stuff with search and advertising, all the things, those have been done. So another aspect of these that's actually really good for research is that the problems in these domains are hard. When I was writing up the summary for this, I happened upon wicked problems definition once again, and when you talk about wicked problems, like problems that are, fundamentally hard, that have to be attacked from many directions, they define it as things that have, either difficult or impossible to solve, but contradictory concepts, many different opinions about the right approach, economic aspects, and they basically are very difficult, but difficult because of the complexity and the multiple different components fitting together. And for AI researchers, this is like, oh, this is great. I only want to work on problems like this because that's essentially the whole idea. You want to work on things that are hard, that people can handle in their heads, but we don't know how to make computers do them yet, right? So an example that I've worked on a fair bit on top of other things is this problem of forest fire management. And this has a lot of different aspects to it. in case you haven't thought about it much, it does boil down to that forests are on fire, and sometimes we want to stop it or control it or mitigate it, or at the very least adjust the impact it's going to have on people who live near the fire or on the economy that depends on those resources. And so it's a big problem in Canada. These are pictures from Fort McMurray in Alberta a few years ago that had a tremendous fire. They had to evacuate the entire city. But as you probably hear in the news, every year the scale and impact of forest fires is growing tremendously. And again, this is actually from a few years ago. It's sad every year trying to update this slide on what's been happening. But every year there's some bigger fire where more people die, especially in California, British Columbia, Washington. But it happens in other countries in the world too, in China, in Russia. Australia has very big problems with grass fires, right? And so there's obviously a lot of motivation there. But in terms of problems and research, what is the actual dynamics of it and how can it be useful for us to move forward? So last year, myself and a bunch of researchers in computer science and forestry science across Canada published this journal paper on machine learning applications in that field. So basically did an analysis of all the different algorithms and problems and domains that are being used where people are trying to use machine learning or AI in this domain. And it's interesting, right? Because in forest fires, what do you have to do? You have to manage a large number of people. You have to collect a lot of information about a complex domain. So in this case, it's the world, the forests, everything going around in your business. It's your customers and your inputs and outputs for your production. But they have a lot of information to gather, right? And they have a lot of people to manage because they have groups of people who can go out and fight the fires. They have analysts who can analyze them. But they need to diagnose, figure out, what's going on right now on the ground, but what's also going to happen next year. How many planes do they need to buy? How many people do they need to train? What kind of resources do they need? So this enormous multi-year planning problem that has long-scale effects and short-term planning problems. And everything's long-scale because trees obviously live a long time, so most models are measured in decades, not in years or months. But at the end, you still have to go out and do things, right? You have to buy those planes, you have to move people from one province to another, you have to decide to fight this fire or not, or clear some of the forest. So it's got all these different levels of complexity, which makes it a very challenging set of problems to do. And so in that domain, people have been interested in artificial intelligence for many years, but they've been very cautious for using it because they don't want black box models. They don't want, they want something they can interpret where they know how it's going to work. They want something that's going to give them confidence intervals that tell them how confident you are in the answer, right? So some kind of probabilities. And they want things that can use the data they have, that they can use with their existing human practices that they've basically built up over the years. But there has been a growing number of publications and interest in using AI and machine learning in this field. So we were doing a review of papers in the field. So that's the number of papers. On the right here is the algorithms people are using. So you can see they're maybe more often using older algorithms. So SVM is kind of the thing that was really popular in the 2000s before neural networks kind of exploded with deep learning. Random forests are kind of a mainstay algorithm that is always working. And some of these other ones are actually kind of older algorithms, and ANNs and I guess the BN involve the deep learning. So there's not a lot of deep learning happening there. People are very cautious. They want a model they can interpret, that they know it's going to work in a certain way. But there's growing interest. So in that, an interesting output for us in that domain was trying to redraw the map of all the algorithms. You've probably seen different maps and trees of how AI and machine learning algorithms can be divided. Everyone has their own way of dividing these up. We kind of devised one because of this literature. So it's kind of got the standard supervised, unsupervised, but also then a whole bunch of things in this agent-based or decision-making approach, which is really kind of neither the other two, because they have to make decisions out in the world and often at different scales of granularity. Like I said, things that were important in the methods they chose were having models that give them lots of confidence, that can be trained without having lots of labeled data, because they don't have lots of examples where they can go out in the world, try things, and then see how it works, because it actually affects the forest and it takes years. So in those easy domains we talk about, like advertising or other things you can do, like testing on users, where you basically try out some algorithm or some approach and see the result. In these domains, you can't do that, right? So we had a bunch of examples of algorithms people were using. So I'm not going to talk about them in detail, but just to show you the variety of things that you can apply, especially when you're thinking outside the box, some kind of spatial planning problem like forestry. So people were applying these support vector machines, which do kind of binary classification on points, trying to figure out which parts of a map have been burned or not, right? And so that can apply to anything that's kind of similar to that. Trying to predict where fires are currently based on satellite images, and where they're going to go next. So having these grids that kind of predict the likely flow and spread of things. Susceptibility mapping, so this kind of can apply to anything where you're talking about susceptibility of an environmental property in the environment, or even in populations. So for drug susceptibility or disease, you'd have similar models, and they have maps around the world looking at the inputs, how they understand how climate affects the ways that the climate would change and how that would affect the ability of things to burn in the future for long-term planning. And then specifically, and it's something we were kind of working on as well on other types of papers, so this is trying to predict where a fire would go literally in the next day or week, given a map and an understanding of where things are currently, right? And we've often tried to think that this could be useful for disease spread as well, if we have the right kind of granularity of data for that. And this is another one where they're trying to look at decision making using sets of trees for different types of policies. But I'll show you, yeah, what I was going to have next is kind of our model of how to break this down. So we have a complex, environment, and this could be your business or some other problem you have in an environment. For us, it's forests, but you have a bunch of input data, right? That is comes from different types of sensors and different timescales coming into your system. And for types of things we want to do, we want to have a simulator that can help us integrate those and see what might happen next. But then improving that simulator is going to be part of one of our aspects of our system. So the next state that would come out of your simulator, you give it an input, a bunch of maps and data that's been collected about the world. The output of the simulator would give you another image or view of that, like a visualization of that map or other numbers, and you get this cycle, right? But then in the middle of that, you basically think about, well, how is this simulator built? What is it? What's inside it? And so the machine learning can come into basically using data to improve that that model iteratively, right? So we want to be able to have it be dynamic, that it can deal with data that is changing over time. In our case, that's weather. In other cases, it might be trends or economic data that you can have coming into your model. But then the actual model about how that simulation works, what happens next in the world, we have to have various prediction systems in there, right? And so I'll just expand this out so I can say it. We have a couple different approaches where we have standard kind of supervised approach, where you get essentially for this, if we have a series of satellite images of how the fire spreads, we could learn how it spreads by that. So trying to use existing data to learn a model of how things change over time. So that's kind of approach. And we have a different approach where we try to pretend we're the thing that's changing over time and make decisions in its stay and kind of learn an AI agent that acts like it. So in our case, learning an agent that pretends to be the fire and tries to learn how it would spread given its goals, which is like trying to spread across space in an efficient manner. And that allows us to use methods like reinforcement learning to kind of spread it. But the other part of the dynamics of any system like this is going to be what you do, right? And so the experts or the people on the ground or your business, what kind of things are you, what actions are you taking? Because that affects what happens next for the next state of the world as well, right? And for forestry, it's going to be going out there and putting out fires and dropping plane loads of water on things, or setting fires in order to reduce them in future years, right? And so there's different levels of planning that can happen here. And this is the part that involves many different levels of government and communities, and get interesting aspects about how you can even make those decisions. So I don't know how much time I have. we looked at a couple of these approaches for the supervised and the decision-making approach. I'll just briefly describe. Oh yeah, so I skipped the supervised part. As soon as give you a brief idea of what we did for this reinforcement learning agent-based model. So we use this model approach called reinforcement learning. This is one of the images I use in my course on it, just to give a kind of fun figure of how it works. It's not that complicated. It's like you've got your model of the world in your head about how you think things work. You take some actions. You see what happens in the world, you get some reward or not, and then you update your model, right? You learn something and you improve it, right? So that's kind of sounds like the way we describe how people and children learn, and that's not surprising because that's how this model was kind of developed, this whole field. Every one of these words has an entire subfield of machine learning you can use to basically improve it. So they're all being revolutionized in the same way everything else is. And the recent advances in it in the last 10 years go back to those things I talked about before, which are kind of fun but not super important problems of playing video games. And they've gotten very good at playing video games using this reinforcement learning recently, which, you know, is fun and impressive from a research point of view, but it's also interesting when you're trying to do something like we're doing with spatial problems, because the video games are spatial. They use the patterns of the pixels to learn a model of how the world works over time by observing it. And they also take action. So if you're playing Space Invaders, you move left, you move right, you see that there's a change in the world, and you learn that by feeding back into your neural network the times that it responded to what you understood it to be doing. And you try to do this in a way that maximizes your score in the game, right? So it's not even have to be some statistical measure. It's like, how well did you do? And so over time, they get better at doing this. So we try to use that for things on satellite images. So we essentially set up a game where the fire is trying to spread across the forest and domain, and we're using satellite images in color and thermal images and other areas, so we can tell when there's actually fires on those maps. And we use that as a way to reinforce a model of that system that spreads in a certain way. Sorry. And so in the end, we get lots of different images of the fire spreading using different types of reinforcement learning, but other types of machine learning as well. In these cases, the red was good, and I think black was good. White and blue are bad because they mean we had a prediction error. So some algorithms work better than others, which is basically what our job is, to figure that out. But that was just kind of one idea of how we can do that. And we're essentially trying to learn an agent that represents this this system, a complex system that we may not be able to model explicitly, but we can learn by interacting with it. So that's just to give you a flavor of that one thing from my perspective of how AI for environmental problems are kind of being used. There's a lot of other challenges, especially in forestry, to do, like logistical issues, economic issues, social issues. It relates to urban planning and risk mitigation, because you may not be able to stop most of these fires, actually. It might be just that, how do you plan so that people can exist with them in a sensible way, and how you can actually take that as part of your planning model as well, and have kind of a game theoretic trade-off between the different issues that people have. But one major thing in this area, which comes up a lot in environmental problems, is trust, right? People don't want a model they don't understand, so you can't just give them a deep neural network that has high accuracy, and it's not gonna make them want to use it. And I'm sure many of you find that also in whatever challenges you're using things for. So a big challenge for everyone is, how do you build a system with the people who want to use the product or the problem in a way that helps them trust that the model is learning from the data that makes sense to them, and is learning something that they think can be used. And so it gets to this idea of trust and interpretability. Now, I don't think interpretability means we have to be able to understand every neuron in the network, every weight, but it does mean we have to be able to visualize it, or somehow explain the different parts and why they're working, and why it makes sense that they're giving the answer they are. And so that's why using human expertise is something we're looking into a lot. Like, how do you take input from various experts with different skill levels, a different expertise in one specific area, and use their information, their knowledge, to help you train a model so that you're confident it's taking all that into account. Yeah, and this is a slide I had usually for this kind of domain about what needs next in this area in general. We need to support human decision making, we need more data that helps us kind of understand these problems better, which applies to any kind of large domain like this. But there's just lots more to do. In many of these domains, people haven't really delved into the latest techniques, and there's lots of potential there, and people are usually very excited to work on it. So I'll end there with that, and thank people and agencies that help support this work that I've been working on. And yeah, we have some pictures. Thank you.
Thank you, Mark. Thank you very much for your good presentation. Yeah, one question, Mark. People have been doing these type of studies, I mean, before advances in machine learning and using data. And now we see complete, I mean, separation from these type of approaches, some of which possibly used to be also quite effective in certain areas. Why haven't people been able to embrace the old and the new to integrate basically data, I mean, analysis, predictive analytics, using machine learning and these type of techniques?
Yeah, it's interesting. Yeah, I don't know. I mean, it's weird. So in this domain, it's interesting because I'll talk to people from operations research in forestry and people who've been doing this for decades and trying to plan this, but from a human point of view. And they're using, you know, optimization methods and like decision trees and kind of classic algorithms that have been developed every decade over the last, you know, long period. And they're not necessarily very quick to add a new thing, but they're using something that's working very well, right? And it contrasts that in kind of the cutting edge machine learning research, everyone wants to do the latest thing because they have to publish, but they're also trying to kind of move on from the old things. And there is, I think, quite a tendency in machine learning research to say, oh, all this stuff's basically superseded. Like no one wants to use SVMs anymore because you can use them with deep neural networks, but they're actually very effective. And you know, sometimes it's simpler, or even logistic regression. Sometimes it's good enough for what you're doing if you don't have a lot of data. So the people in this field are very willing to do that. They're always suspicious, like, why neural network? I can't read anything. That I think that's the thing that that's why it's useful to talk to people in these domains.
Mark, since this is an industry day, do you think that people who are in the area are able to get insights from machine learning, from data analytics, from AI tools? I mean, a lot of them are not educated or not, they are not raised to be managers in these fields and they don't have background. So how do you see these people could get the best out of the machine learning field to solve these type of problems?
Yeah, no, it's challenging. I think, what seems to work well is when people are working closely with someone. So you have a project and you say, okay, we're going to do this together. And then you have a dual team of like the expert in the domain and the expert in machine learning, and they both try to understand each other, right? I'm doing that with things with like chemistry and for forestry and stuff. And that seems to be the only way, because you don't want to assume that someone's domain is so simple you could just kind of read up on it and then come up with something. There's always some, especially things like this, there's so much complexity built into it. So yeah, I think it's just, you need a team, because no one has any time to learn, be an expert in both fields usually. Although we have a new project where we've got some funding now for like strategic network for this forest fire and AI and data analysis to basically try to train up some people who at least have a bit of both skills. But then they basically have to do a degree in it, right? Get a graduate degree. That's
the idea. Yeah, the idea is to train new people. In these particular areas who might become some of the next generation, future generation.
So somebody wants to do grad studies
connecting them with us. Very good. Yeah. Thank you, Mark, very much.